Our next speaker is, many of you know Steve Bertman. Steve's been a longtime researcher at the station. He was one of our co-directors of our IGRT program, the Biosphere Atmosphere Research and Training Program. Some of you actually were part of that program. And he's also working with us next summer to co-direct our REU program, which I failed to mention early on, but we will, I assume and hope, be trying to renew that grant, Research Experience for Undergraduates. So we're loading Steve's presentation in right now, so we can mic him up.
Great. So I'm not going to show much data here. Sorry.
It's the down.
The down. Okay. So I just added this morning. So we've been the program for research on oxidants, photochemistry, emission, and transport. We've been the PROPHET project. We're approaching our 20th anniversary, which is kind of remarkable to me. We've been studying atmospheric chemistry for almost 20 years at UMBS, and when we first, I think of it sort of as hurricane prediction. When we first descended, this invasive species of chemists descended on the biological station, there was little warning in 1997, and there was some shock. I think so. I'm thinking of this presentation as the technology for prediction has improved. This is a warning that this summer, PROPHET is coming back to UMBS. It's down. So here's the weather prediction model forecast. We are going to be measuring we're trying to get 4 weeks of intensive measurement at the PROPHET lab for essentially the month of July. So people will start showing up at the end of June, and will probably stay just it takes a little time to tear down at the beginning of August. So that's when PROPHET will be there. We're expected. This is a collaborative effort. We have 17 institutions that have been funded to come and make measurements at the PROPHET lab. We're approximating about 40 people. Not all of them will be there for the whole time or at the same time, but they'll be focused at the beginning and at the end. But there will be a steady state of atmospheric chemists. From 17 different institutions, I've listed the institutions that are involved on this list. It's a little bit more challenging, or at least it has historically been a little bit more challenging to develop the kinds of collaborations that Paul and Luke and Tim have described before me. Because it's sort of like a locust infestation, right? We come, we swoop down and leave. But there are a lot, we're very interested in understanding interactions between the biosphere and the atmosphere. And we understand the atmosphere side a little bit better than the biosphere side. So we encourage and welcome any suggestions or questions about how our work can mesh with the work on the biological side to better understand the gas exchanges and the effect of gas or atmospheric transformations of material on the biosphere. And now just a little lesson in atmospheric chemistry. I apologize to those who may have seen a version of this before, but We are interested, we're concerned about pollutants that get emitted into the atmosphere. Think about two major classes of pollutants: organic material, reduced organic material that fuels chemistry in the atmosphere, and nitrogen oxides that catalyze the chemistry. In a way, nitrogen is a limiting nutrient in the atmosphere for atmospheric chemistry, as it is in, as I understand it, many of the terrestrial ecosystems at the biological stations. So these two reactants, when shined upon by the sun, make a whole soup of products that we refer to as photochemical smog, largely characterized by the presence of ozone. So that's what I listed there. So these three components combine, and we make ozone for a long time. Certainly when it was discovered in the early 1950s, it was assumed that this was an urban issue. We have since learned that other things put stuff into the atmosphere other than cities. And so we've been focusing on for the last couple of decades on understanding the effect of biogenic sources of not so much the NOx, although there is some question about that, but primarily VOCs. And in addition, we've begun to focus not only on the gas products of the atmosphere, the photochemical smog, but also on the particles. So we understand a lot of the gas-based chemistry that occurs, where the frontier of our understanding of what's going on in the atmosphere is largely here, understanding how all of this interacts or affects small suspended particles that we refer to as aerosol. And so how important are the biogenic sources in this mix? Just to give you some perspective, VOC emissions, total VOC emissions in North America at least, are estimated at about, say, 100 teragrams of carbon per year. That's from anthropogenic sources, from urban activities. Biogenic sources, at least 5, maybe 10 times, depending on how you measure. So biogenic emissions of VOCs far outweigh by mass the amount that's put into the atmosphere by urban activity. If we look at the breakdown, we see that the lion's share of this biogenic emission comes in three forms. Isoprene is half of all of those biogenic emissions. Another quarter is in the higher terpenes, like the pinene, and then oxidized products or oxidized forms of these terpene compounds, which we know very little about, primarily because they're in very small concentrations and they're very difficult to measure. We haven't had the capability to reliably measure them for a long time. For those chemistry geeks in the audience who want to see what those structures look like. So this is the isoprene, that's half of that pie of the huge amount of biogenic emissions. Two isoprenes will make a monoterpene, and there are dozens of ways you can take two terpenes and put them together and say we got all of these isomers, alpha-pinene being the largest in the forests. In the forests of UMBS, alpha-pinene is the largest concentration of monoterpenes. And then take 3 isoprene units, you get sesquiterpenes, or you get diterpenes, and so on and so forth. Once they start getting this big, they're not very volatile, so that we don't see concentrations of them in the atmosphere. But the bigger they are, the more likely they are to form particles. And so what we are investigating is the conversion of particles or gases into solid particles. And there are a range of different biosphere-atmosphere interactions that are affected by the conversion of gas emissions into particles. One of which is that particles, well, of course, particles are one of the largest uncertainties in climate models, both the direct and indirect effect of particles. They can seed the formation of clouds. They can also directly either reflect or absorb radiation. Certainly can change the amount of light that leaves at different parts, different places, different heights in the canopy. There's evidence that diffuse radiation actually penetrates the forest canopy better than direct radiation, and so we may see an effect. Increased atmospheric particles may change the relative growth of the understory versus the overstory in forest. And of course, there's direct effect on climate, potentially. That direct effect depends on the composition of the particles. Higher organic fraction in the particles will absorb more infrared light and reflect less, so we'll have a net warming effect. So the composition of the particles is important, and our ability to predict when they will form and what composition they will have when they do form and where they will be distributed and how long they will live in the atmosphere. These are all questions that have direct bearing on forest productivity and ultimately on a larger scale climate. So we want to understand the fundamental mechanisms that will allow us to predict how these particles will form. And we're doing this study, of course, in a context of a changing climate. And as Chris will tell you, in a context of a changing forest. Love this picture. I show it every chance I get. But I do.
My 7th grade art skills.
Yeah, it's great. I like it. That's about my level of artistic appreciation. And so the climate is changing, the forests are changing, and with those changes come changes in VOC. So we're seeing, for instance, not every tree emits the same compounds into the atmosphere. So white pine trees tend to produce more monoterpene alpha-pinene. The existing dominant aspen overstory primarily produces isoprene. These two compounds react differently in the atmosphere. And so with all of those changes come changes in atmospheric chemistry. So it's really important for us to not be completely phenomenological about our study. We need to be mechanistic. We need to understand the underlying processes so that when conditions change, that the processes, the fundamental reactions aren't going to change. We'll be able to predict what changes will occur. So this study, as many of you know, is a very instrument-intensive study. It's a little bit different than a lot of the ecological studies that have been done. Students tend to come up and have to babysit their instruments 24/7. But I encourage anyone who's interested. Some of these are research-grade spectrometers that we've never had at profit before, that are just being developed. We're going to call a chemical ionization mass spectrometer to the top of our 100-foot tower, and they tell me it weighs 1,000 pounds. Coming from California, I guess everything's bigger out in California. So that gives me a little bit of heebie-jeebies, but so I tried to summarize. So there's 17 different groups. Each group is funded for their specific part of the project, but there is an awful lot of synergy within our group. And I've tried to list here some of the unifying large-scale objectives and which group is going to be contributing to which of these objectives. This is a gross oversimplification, but it gives you an idea that we're going to be looking with some high-powered lasers at the fundamental radical chemistry, how these radicals are formed, what they do in the atmosphere, how long they live. We're going to be looking at total reactivity, trying to achieve mass balance between reactivity and what we can measure in terms of concentrations. We're going to be doing a lot of work on BVOCs, the biogenic VOC compounds, and how they are related to particle growth. We're going to, with a lot of focus on those oxygenated products that were about a quarter of that pie that we didn't have the capability of measuring before. And then there's a whole team that's going to be simultaneously measuring fluxes of gas-phase nitrogen compounds from the soil, within the soil, out of the soil, into the soil, into the free atmosphere. And again, because nitrogen is a limiting nutrient in the atmosphere, it's really critical to understand how it gets partitioned into the ecosystem. So I think I would again encourage you to think about ways that what we do can at least inform your classes or your research, and would love to have you come out and visit the tower.
Thank you, Steve. Thanks a lot. This is time for a comment or a question or two. Or one? I have a comment that I know is on a lot of people's mind, including yours. We have been successful in hiring 2 research scientists at the station, Luke Nave and Paul Bertman. We still have a priority of hiring a 3rd. Literature, science, and the arts. Cost share with another unit to recruit an atmospheric scientist. An effort like this is incredibly important and complex, and Steve and a couple close collaborators are really doing all the coordination work, but there's really niche space for an atmospheric scientist to round out this triad of terrestrial, aquatic, and to be named atmospheric scientists. Of course, we'd like to expand beyond that and have more organismal people at the station too, but we go in a stepwise fashion. So if your unit, if it's the College of Engineering, which now has a new dean as of this morning's announcement, yesterday's, or the School of Public Health, or any unit on campus is interested in potential to collaborate on recruiting a research scientist to help coordinate and build their career doing research at the station, invite your chair or dean up. Firsthand, see what this group is doing in terms of bringing an international group of people who are doing state-of-the-science work. But we do want to recruit that person. It takes another commitment from another unit.
Because you said you've been doing this for 20 years, whether that change in the composition of the volatile organic carbons with change in forest composition is a hypothetical, or is that something you actually see?
Yeah, that's a good question. So when we first, in 1997, we focused largely on characterizing the atmosphere and the dynamics with weather patterns and things like that. We have a lot of isoprene measurements from that time. Because these are research grade instruments, we don't have them continuing, so we don't have a continuous record, and there really is a dearth of BVOC measurements over the years. So our data is somewhat limited to answer that question. Some of it is theoretical, some of it is based on actual measurements of actual leaf composition as opposed to gas phase. But there is, so we have limited information that the concentrations are changing. What we'd like to do is to be able to answer that question.
Just to
follow on that comment a little bit, Steve, something to think about is the aspen and birch have faded, or are fading from the canopy naturally. 97, it's about half.
Yeah.
Half, right, as far as leaf area, half the aspen and birch represent.
In the entire, you think in the entire landscape?
Yeah, we have data, so that might be interesting.
Yeah.
Where's the maple, right, and oak are tracking up?